All right, let's get right into it. Today we're talking about something called immunopharmacology. It's the incredible science of using drugs to control the most powerful force inside your body, your own immune system. You know, it's designed to be our ultimate protector, but sometimes it really needs to be reined in.
So just think about this for a second. What if your body's best defender, the system that's supposed to keep you safe, suddenly became your worst enemy? It's a terrifying thought, right? And that's the exact problem immunopharmacology was created to solve.
So when does this happen? When do our good defenses go bad? Well, there are two main scenarios where we have to find a way to tell our immune system to, just stand down.
See, our immune system is kind of like a double-edged sword. On one hand, it's the hero, fighting off infections and keeping us healthy. But on the other hand, it can turn into the villain, attacking our own healthy cells, rejecting a life-saving organ transplant, or causing all sorts of chronic inflammation.
The first big problem is something you've probably heard of: autoimmunity. It's basically a case of mistaken identity. The immune system gets confused and loses its ability to tell the difference between you and a foreign invader. So it starts attacking your own healthy tissues. This is what's behind diseases like rheumatoid arthritis and lupus.
And then there's the other huge challenge: transplant rejection. Now, you'd think your body would be grateful for a new kidney or a new heart, right? But to your immune system, that new organ doesn't look like a gift of life. Nope. It looks like a massive foreign threat, and it launches an all-out war to destroy it. This is where these drugs become absolutely critical.
And all of this leads to the central challenge of immunopharmacology. It's this incredibly delicate balancing act.
So here's the tightrope you have to walk. You've got to turn down the immune system just enough to stop it from causing damage, but not so much that you leave the body totally defenseless against every little bug that comes along. It's a constant, high-stakes balancing act.
Now, to handle this, doctors have what you can think of as a toolkit. It's full of different drugs that all have their own unique way of telling the immune system to just, take it easy. Different tools for different jobs.
First up in the toolkit, you've got the sledgehammers. We're talking about corticosteroids, like prednisone. These things are incredibly powerful, and they work by just shutting down a whole bunch of genes that cause inflammation. They get the job done, but they're not exactly subtle about it.
And because they're such a blunt instrument, you see them used for all sorts of things. They're a go-to for stopping transplant rejection, calming down autoimmune flare-ups, and even tackling severe asthma or allergic reactions. When you need to shut down a crisis fast, you bring out the sledgehammer.
Okay, so let's get a little more precise. Next up are the signal jammers. A classic example is cyclosporin. Now, instead of a sledgehammer, think of this more like finding the right wire and snipping it. These drugs work by blocking the ghost signal inside T cells, the generals of your immune army, and stopping an attack before it even starts.
And you can kind of see how it works right here. Cyclosporin gets inside the cell and basically grabs onto a key protein called NFAT and physically stops it from getting into the cell's nucleus. If NFAT can't get in, the cell can't make interleukin-2, which is the chemical messenger that screams attack, so the signal gets jammed. It's pretty cool.
All right, what's another tool? How about the proliferation blockers? If the immune system is trying to build an army, these drugs, like mycophenolate, are designed to cut off its supply lines. They stop the army from ever getting big enough to cause a problem.
The strategy here is really clever. The drug blocks a very specific enzyme which starves the immune cells of something called guanosine. Now, guanosine is a critical building block for making new DNA, and it just so happens that your T and B cells are super dependent on this one specific pathway. So you cut it off, and they simply can't multiply. No reinforcements for the army.
But, and you knew there was a but coming, right? Forcing this kind of truce on your immune system, well, it comes at a price. Taming the body's fiercest defender has some pretty serious side effects.
Let's just take cyclosporin, one of our signal jammers. Look at this number. A staggering 50 to 70% of people who take it end up with high blood pressure. I mean, that's not a rare side effect. That's more common than not. It just shows you how much these drugs affect the entire body.
And yeah, the list goes on. Kidney damage is a huge one. So is developing diabetes or having your bones get weaker. Even serious mood changes can happen. This is that price of peace that patients and doctors are constantly trying to manage.
And some of the risks are so severe that they get the FDA's strongest possible warning, a black box warning. When you see this, it means there's a risk of really serious, even life-threatening harm. For a drug like mycophenolate, it's because it can cause severe birth defects, which makes strict precautions for patients an absolute must.
But really the biggest risk of all,
the one that comes with every single one of these drugs, is the very thing they're designed to do. A suppressed immune system is, by definition, a weakened immune system. This leaves patients wide open to what are called opportunistic infections, things a healthy person would fight off without even noticing. And over the long term, it can even increase the risk of certain cancers. So, with all these serious trade-offs, the mission for scientists has always been clear: get smarter. We need to develop therapies that are way more precise and a whole lot safer.
And this chart really shows you that evolution in action. We started with the sledgehammer of corticosteroids, which just hits everything. Now we're moving towards the scalpel of modern biologics. These are engineered drugs that are designed to target one very specific molecule involved in inflammation, like TNF-alpha. It's the difference between carpet bombing an entire city versus a single precision strike.
And this incredible precision really is the future. It's where the whole field is headed. And it leaves you with a really exciting question to think about. As our toolkit gets more and more precise, moving from sledgehammers to scalpels, and who knows, maybe someday to nanobots, what diseases that we think of as incurable today might we finally be able to conquer?